All right. So I will start on. So I'm really looking at how do we move things to practice. That's been mainly what I've been trying to do in the last 20 years of figuring out how to take pieces that are ready and start to move them into practice. So we'll talk about this. So we see this is on the right-hand side, the 3D simulations from Hayward, and the same idea of just saying, look at all this variability and what happens and the complexity. On the left-hand side is our same thing, same scenario, but from a ground motion model, but it's just the median ground motion. And it looks smooth, but our models really aren't that smooth. Jack Baker talked about all the, putting in correlation and the variability. So if we actually made a realization of a single event on the left-hand side, it would have all sorts of highs and complexity, highs and lows in complexity, like what we see on the right-hand side of the model. So in the end, for us, for seismic hazard analysis, having a small number of realistic simulations isn't enough. We have to have models that are mean-centered with uncertainty. And we've talked about that before. We need the median and the epistemic uncertainty of the median, and we need the standard deviation or aleatory variability and the epistemic uncertainty in its value, right, its size. So we need all those pieces to run hazard calculations. Our current practice using ground motions, right, we use a median. Our centered model is the weighted average of alternative ground motion models typically. Our aleatory variability is from our empirical ground motion models that are single-sided in a single period. And then the correlation models that Jack Baker talked about can be used to estimate the pairs or suites of ground motions at multiple locations in a single earthquake and the period-to-period correlation at a site. And then our epistemic uncertainty, we're just using alternative ground motion models to get the range, and we might have separate them into alternative median models and alternative standard deviation models. But we get all the pieces that we need to run hazard. So why don't we just start using the 3D simulations directly? And CyberShake is sort of the first big calculation to do that, where it says we'll just completely replace the ground motion models with 3D simulations and run the problem going forward. So the issues are, we talked a lot about, we need adequate validation, right? The current validation exercise that we had from SCEC that was done 5 years ago is limited to the median and 1D simulations. And now we need to do validation of the medians from 3D simulations and also the variability. If you want to be able to move this, take these ground motions directly into hazard, we need to trust not just the average values, but the distribution of the ground motions. For hazard use, we need to separate path effects from the variability of the source effect. So a systematic path effect is going to affect the median. Variability of the source effects belongs in the aleatory variability. So we need to be able to separate those out, which means, again, enough realizations of the source. So we're averaging out the source variability and isolating just the systematic path terms. And then we need to have the epistemic uncertainty in the base source scaling model. So in the empirical world, we use alternative ground motion models that may have different assumptions or on how they extrapolate and how we get up to large magnitudes. But here we have to have some uncertainty in how things scale. So we need, say, alternative rupture models or models for rupture generators, and then looking at how the medians from the different 3D simulations compare. And I talked about this a little bit this morning. And then our other issue of not using these all directly, again, comes back to the truncation of the profile that we've talked about quite a bit. So the first step in moving to implementation is we need to demonstrate these simulations are no worse than empirical models. So my criteria is not that high, right? You can't be doing worse than our empirical models. Having it be physics-based is not enough. It's nice, but it's not enough for us to take and use it in practice, right? So you have to compare with observations and demonstrate that it's working as well as the empirical models. And to the issue of, this comes back to really, is this current 3D velocity model good enough to actually give improved estimates of the ground motion compared to the empirical models? You might have all the right physics and our 3D model just is not accurate enough and it's making things worse, right, than something simpler. So this has to happen before, in practice, we're going to start to take these and charge forward. The comparisons with the ground motion models have two parts. There's the ergodic ground motion models, but we now have non-ergodic ground motion models for California that can be used. And these non-ergodic ground motion models are going to be closer to what the 3D simulation is trying to do, but they're going to be basically based on small magnitude data that contains linear path effects and side effects, and without modifying the source term. So those two things, you need to be better than the ergodic ground motion models, and we should compare them to the non-ergodic ones to see if you're doing better than those models. So not a really stringent criteria, but it has to happen or this just won't move forward. So this is a really busy slide on this sort of phased implementation. And by phased implementation here, I'm talking about how do you start to move forward rather than saying, let's keep doing research and we're not all the way done. What can we use from what's available now? And how do you move this forward? So phase one on the top, we're only going to take the simulations to adjust the median for path effects. Okay, and this is essentially what's being done with some of the 3D simulations that are used for basin effects. So we would look at the differences between 3D and 1D response and the models, but then we would use our epistemic uncertainty. We'd use the empirical range that we've got already that we currently use in seismic hazard, and the aleatory variability would still be based on empirical models. Here, I put them using the non-ergodic ground motion models because they ought to be the aleatory variability that goes with knowing the velocity structure, right? That it's not, that we actually have site-specific and path-specific effects in the model. So that phi naught that we have there is our within event variability term for a model that has path effects in it. The second part, phase two, we would have the simulations used for the median. So now we're going to trust the median from the simulations itself. So both for the path and for the source effects that are there, and using the epistemic uncertainty from these 3D simulations. What's the range? So we've talked before that epistemic uncertainty of the median requires a bunch more simulations and comparisons of different models and adequate validation so we can see the potential error in the model or misfit and bias. But we'd stick with the aleatory variability being empirical. Okay. In the end, aleatory variability is going to have to be something that is calibrated empirically. It's driven by what is variability, and we need to sort of make the first steps here are we keep using empirical numbers, which are pretty stable. Then in phase three, we would start to take the median from the simulations directly and the standard deviations from the simulation. So that's going all the way to, for example, the CyberShake approach of using the simulations for all parts of the model. So when we're trying with phase one to get started, we're going to, again, use the simulations to here put adjust the median from an ergodic model for 3D path effects. So we need to isolate the path effects. And our goal is to remove the differences between the sources models, source scaling in the simulation and the source scaling in the ground motion model. So we're going to keep the source scaling in the ground motion model in this step and account for, though, the truncation of the low VS values, right? So the truncation of the velocity structure has to be dealt with. And then, as I said before, we're using non-ergodic models for the aleatory variability. So this is really similar, again, what I wrote at the bottom, to what's done when we take 3D simulations and try to correct seismic hazard maps for basin effects. The difference is that we're going to change the standard deviation from the empirical model to not be an ergodic sigma model, but to be one that goes with, accounts for the reduction in the standard deviation when you have included path effects that should be improving the accuracy of your models. So when we do this, how can we make this work? So I have two alternatives for this first phase. And when we move slowly, you have to have several different adjustments in there, and it kind of gets a bit clunky, but we need to put all the pieces together. So we could start with our ground motion model ergodic, and then we're going to look at the ratio of our 3D simulations with that truncated profile over our ergodic ground motion model with a non-truncated profile. we can't put truncated profiles into the ground motion model because the VS30 scaling in the ground motion model is not a fundamental physical behavior of site amplification. It's simply correlated with, it's an empirical correlation with the deeper VS profile that controls the amplification. And that empirical correlation is from the surface. It is not from a truncated profile. So it doesn't work to plug in truncated profiles into the ground motion model. Then we have to have something to try to account for that truncation. And so we can look at what's the we're back to scale factors on how this response spectrum changes if we had not truncated it versus truncating it. This doesn't, though, account for differences between the sources in the simulations and the ground motion model. So if there is a difference in the sources, in this case, we would be effectively mapping it into what we're calling here the path terms. So when we're looking at the truncation of the profiles, on the left-hand side is velocity profiles, and it's probably confusing because the axis on depth is in log units because we wanted to be able to see the top part easily and what's going on at depth. But this would be the velocity profile, for example, from the USGS 3D model for the Bay Area in blue. And on top, we take that and we truncate it, let's say, at 500 meters per second. So to get this correction, we're going to take a input at depth, the same input, drive it up through the orange truncated profile, drive it up through the blue profile. We get response at the surface, and we take the ratio here, or the difference in the logs of the response, and that's going to be our site correction factor that's then applied. The other way we can do it, approach 1B for phase 1, is to take that same ergodic model, but now take the 3D simulations and divide them by 1D simulations that use the same source. And the idea is we're going to try to cancel out the source effects so that we're going to isolate path effects here. Artie Rogers has done some of this. What I'm going to put here is a little bit different on how you address the issue of what you're normalizing by is not the same as the ground motion model. So the first thing we have is accounting for the differences between the 1D profile that you've used for a reference profile that's used everywhere and what the ground motion model would be giving for the VS30 at that particular site. And we'll go get this more in detail. The second part here is a piece on the path effects, and that is the distance scaling in the 1D simulation may not be the same as the distance scaling in the ergodic model. And we don't want to, that difference is going to show up in the denominator, and we don't want to map that into what we're treating as path effects. So we take out the difference in the average distance scaling, not to a site, but over the entire region. And then we have this same correction we need to deal with the VS30 time. If we're looking for how do we correct or deal with our normalization was a 1D profile that was the same everywhere. We could have, for example, this blue line might be a velocity profile used in the 1D simulations. And then if I went to my ground motion model and I had here even a similar VS30 value for that particular site, this profile in red is the profile that's implied by the scaling in the ground motion model. So we're working on starting to produce these going forward. So a ground motion model, when we tell you the VS30 equals 400, it should also tell you the velocity profile that goes with that model, which is based on the scaling, the period-dependent amplification that comes out of the ground motion model. And then we're going to do the same thing, input a same motion at depth through the two profiles and get the ratio. We'll get the amplification here, and the ratio of those two amplifications, or what comes up at the surface, is our correction that we're going to be applying. So that gets us back to our ergodic model. We're having our 3D over 1D effects. We're correcting for the difference between what's in the ground motion model, VS profile for that VS30 compared to what's in the 1D simulations. We don't want to map any differences, average differences in the distance scaling, and the same truncation part. So there's a lot of corrections to this, and it seems kind of clunky, but if you're trying to move slowly, that's sort of what you have to do to try to do all the pieces one thing at a time. Phase two, so phase one is something we should be able to do now. If we can get through an initial validation and demonstrate this is working better than the ground motion models, or as I said, no worse, we should be able to do that in the short term. Phase two is now going to use it, the 3D simulations, all the way for the median. So I'm just now trusting both the source and the path types. And this has to get to a validation of the median for the 3D simulations. So we've got to get through that process. And we want to have, in a way as well, these are typically run for just a small number of key scenarios, like magnitude 7 on the Hayward Fault. Maybe you're going to run a magnitude 8 on the San Andreas. What do you do to get other scenarios? So we have to have some scaling to adjust this to other parameters. So we can use the ground motion models to help guide that extrapolation on how we're going to scale the models. So in this case, instead of using the ground motion models with scaling from the simulations, we're going to use the simulations with scaling from the ground motion models to move forward. And we're still using that empirical models for the aleatory variability. So this is all feasible if we can get to having the validations really complete, and we say the medians from both the source and path are unbiased. So in this, we have our simulated from our VS truncated profile, and then all we need to do is put in our correction for the truncation part, right, for the profile. And then there's a term here that I just wrote. This is going to help us extrapolate the scaling. So there'll be magnitude dependence in here. There may need to be a distance term if there's a distance dependence with magnitude that allows us to extrapolate this scenario to other magnitudes. So then phase 3 is getting to using the 3D simulations directly. And this is what most of you envision as, here's what we should be doing, and let's charge forward. I think this is still several years off, but we ought to be getting started and moving down this direction. So in this case, we would still have 3D simulations for key scenarios. This should have been, we're going to have them for more scenarios to go forward, but we're going to use them both for the median and we're going to use them for the aleatory variability. So after we get this requires completing the validation of the aleatory variability part that we haven't been doing yet. And this may differ from log normal in the tails. I know Brendan had talked about trying to get the simulations to be log normal, and in the middle part of the distribution, I agree with that. But at the tails, there may be differences. We see, for example, fat tail distributions in the empirical data above 2 standard deviations, and it would be good to see if the simulations are also telling us we're deviating from log normal at these really high levels. What does a really rare ground motion look like? So phase 3, we're just taking the values, truncated values directly. We've got enough simulations to run, and then we're going to just account for the VS30 part. I saw 2 versions of this in terms of how we're going to treat the aleatory variability. One is probably it's easiest on the validation to get at, is the average right? So if I run the simulations and I'm looking at a lot of sites, is the average variability from the 3D simulations appropriate? And just use that average from all sites and apply it everywhere. So that's kind of how we do the ground motion models now. The next part, 3B, we could say we're going to take the site-specific aleatory variability. So one location may become, let's say at the end of a fault, maybe is more variable than a location near the center of the fault. And you should be able to then model that behavior. Okay, so a summary of what we're talking about here, the phase 1 is going to use simulations only for the path effect for the median, empirical models for the epistemic uncertainty and aleatory variability terms. Phase 2, we use simulations for the median for source and path for a limited number of scenarios. Okay, sticking with the empirical models on the aleatory part. In phase 3, we have a larger number of scenarios so that we can get all of the magnitude scaling out of that. We have then simulations enough to get the epistemic uncertainty, and we're going to believe the simulations for their aleatory variability as well. So how do we get there? So phase 1, again, we have to do an initial validation the simulation, 3D simulations for median path effects. And by median path effects, I mean, we're going to allow the simulations to be systematically higher or lower than the observations, and we're not going to worry about that term because we're just after the path effects. Okay, so we need 1D and 3D simulations to be able to do that sort of validation step. The next, phase 2, we have to complete the 3D validation for simulations for the median for both the source and path effect. So now not shifting anything by a constant, but all the median values right. Okay, and then we're going to complete the validation for the aleatory variability for a region from phase 3. And then we need a much larger number of simulations to start to get this done and for more scenarios. And then phase 3B, we have to look at validation. Are we actually able to get variability at a particular site? This needs a data set like, I guess, what was being discussed in New Zealand, where you have enough recordings where you can start to see variations in the aleatory variability from one location to another. We've started talking about that term in ground motion models. Rather than a single sigma, I have a sigma at a site, and how does that vary? So if you have that kind of data, you can see, are the simulations producing the same kind of a pattern of increased variability at some sites and reduced variability at other sites. How many realizations do we need to get this going? A really simple way we look at it is just from our non-ergodic ground motion models. We can see what is their standard deviation after I remove systematic site and path effects, leaving in source terms still. And those numbers are in the sort of 0.4 to 0.5 range. And so just a simple standard error of the mean, if you want to get this to be less than 0.1 or 10% uncertainty in the median, we're going to need numbers here like 20 to up to 30 simulations to be able to get there. Okay, so I think phase 1 we can start on, and my main push here is it's time to get started and not just keep talking about this. How do we get this into practice so that people running hazard can start to actually use these approaches? But this initial validation has to be done to just demonstrate that there's an improvement, or as a minimum, no, you're doing no worse than the current model. So do no harm in moving forward. Phase 2 is going to require more additional validation and more scenarios. And then phase 3 is going to be this big increase in the number of scenarios and how many realizations we're doing. And that's going to get to this whole idea of either faster computers are going to help us and more efficient methods, like we talked about this morning, on how you can try to generate more realizations looking at some alternative approximate methods. All right, thank you. Am I on time?
Very good, Norm. Thanks. Right on time. Just a reminder, we're going to go on to the